All right, the last thing we're going to cover in this chapter on phase diagrams is an example of probably the most important phase diagram to material scientists, which is the iron-carbon phase diagram, and that's the one that gives us steel. So the steel phase diagram is fascinating. First off, let's just take a look at it here. Here I've shown it. What do you see? Do you recognize any of the reactions that we've learned about? Well, what about eutectics? Do you see any eutectic reactions? How about right here? A liquid turning into two different solids, gamma plus Fe3C. We call Fe3C cementite, by the way, and gamma we call it austenite. That's the austenite phase. So right there at 4.3 weight percent carbon, if you cool it down at 1147 C, you get the eutectic formation of cementite and austenite. There's one. What else do we see? Well, how about this reaction over here? That one in that top left corner at 1493 Celsius. Well, as you cool it down, you're going to have a mixture of liquid plus this delta phase. So at that point, you're going to have liquid plus delta turning into austenite. So that's a liquid and a solid turning into another solid. We call that a pereutectic point, right? So that's a pereutectic. What else do we have? How about right here? Cooling it down right there at 0.76 weight percent carbon, we go from pure austenite into a mixture of ferrite and cementite, where the alpha phase here is the ferrite phase. So one solid into two other solids is a eutectoid, right? Gamma turning into alpha plus Fe3C, that's a eutectoid, right? So a lot of cool reactions happening in this diagram. Now, if you go just below this point, from across that eutectoid, let's say you were right here, right? You're going to end up with a structure that's a mixture of ferrite and cementite. And just like before, the eutectic structure forms a lamellar structure, you're going to get the same thing. So just above, this is at T above 727 degrees Celsius, you're just going to have grains of the gamma phase, austenite, right? But then at T just below 727 Celsius, you're going to end up with all of the austenite is going to be gone, right? Because the eutectoid reaction took place. And so now you're going to have in these regions a mixture of ferrite and cementite. And it's going to be this lamellar structure because it happens so quickly. Okay? So just like we saw before, you're going to see this lamellar structure. Now, to the left and the right of that point, we end up with hypereutectoid and hypoeutectoid compositions. So hyper means you've got too much carbon, so those are going to be greater than 0.76 weight percent carbon, right? So your hypereutectoid steels are going to be over here on the right-hand side. That's your hypereutectoid. And then to the left, you've got your hypoeutectoid steels over here, okay? Hypereutectoid and hypoeutectoid compositions, okay? Now, iron, when you go and you buy iron at like Home Depot, it's going to have very small amounts of carbon in it. We want it to be flexible. We don't want steel wire sometimes. Sometimes you want iron wire, right? So that's going to have less than 0.008 weight percent carbon, right? Because there's to get this pure ferrite phase, you don't have very good solubility of carbon in that phase, okay? Now, steel is anywhere between this the iron region, so 0.008 and 2.14 weight percent. So your steels are going to be in this region right here. That's where your steels are, right? All the different steels that you can buy. And then your cast irons go all the way 2.14 up to technically 6.7, but usually around 4.5. So this region through here, these are your cast irons, right? So when you buy a cast iron Dutch oven, it has much more carbon than any of the steels that you're going to buy. Now there's consequences to that. What do we know about these things? Well, clear over here, pure iron, right? This is iron with just a little bit of carbon. That's going to be very ductile. You can bend that wire really easily. But over here, this Fe3C, that's a ceramic. It's a full-on ceramic. It's a carbide at that point. So it's going to be very hard, high melting point, very tough. Not very tough, very hard, very refractory. Not ductile at all. And then in this region where you have both of these, the ductility and the hardness of your alloy is largely a function of how much of these two phases you have present. So if you're more on this side, more on the low carbon steel side, you're going to end up with a more ductile alloy. Where if you're on this side, more on the high carbon steel side, you're going to end up with something that has more of the hard, brittle ceramic phase to it, and so it's going to be a high hardness, low ductility alloy, more prone to fracture, but stronger. Okay, so you can learn more about these, and we will in a later chapter, but you've got your low carbon steels. They're mild steels, low cost, easy to shape. They're not very hard, but you can do things to the surface like carburize the surface. We will talk more about that when we talk about diffusion. You've got your medium carbon steels. These are between 0.3 weight percent and 0.8. This is like a sort of good combination of ductility and strength, and they have pretty good wear properties. Finally, you've got your high carbon steels between 0.8 and maybe 2 weight percent. Very strong, really cool things. And then you've got ultra high carbon steels. Really, these are cast irons, extremely strong, but they are brittle. Okay, so we will talk a little bit more later in this semester about the different microstructures of steel that can happen. Because so far we've shown you that you've got, alpha plus Fe3 in this whole region. This whole region here is just a mixture of alpha plus Fe3C. But in fact, there's lots of different ways that you can get that to occur. So we will come back to that and talk about the difference between, say, pearlite versus bainite versus spheroidite. We will come back to that later once we talk about kinetics. So just put a pin in that for now. Okay. So what would the structures look like if you cooled the structure down in the hypoeutectoid? Hypoeutectoid means that we're cooling it down to the left of the eutectic, right? So over here somewhere. What will it look like? Well, it's going to pass through this intermediate region right here, right? As it passes through that region, it's going to form alpha plus austenite. So some of your austenite is going to turn into alpha ferrite, right? So if we cool it down, it will look like this. So it starts out fully austenite, so everywhere is austenite, and then as it cools down, you're going to form ferrite. Now, where will the ferrite form? If possible, it's going to want to form along these grain boundaries. Why? Why does it want to form along the grain boundaries? It wants to form along the grain boundaries, so this is the ferrite that's forming initially. It wants to form along the grain boundaries because remember, the grain boundaries cost us energy. If you zoomed in on this, you had atoms arranged in one way, atoms arranged in another, and then you had this nasty sort of interface where they couldn't form nice bonds. So that surface was already costing this compound energy. And so if you're going to form a new surface, you might as well get rid of an old surface, right? So now you've got a surface on this side and on this side, but you've got rid of the old one. Anyways, new phases like to form along grain boundaries if possible. Now, in order for that to happen, you have to diffuse atoms to or away from these regions, from the bulk. Maybe you have to diffuse it away from there or to it. And if your diffusion is not fast enough, then you won't be able to do that. Instead, what you'll form is this alpha phase forming as precipitates. We'll talk more about precipitate hardening in a later chapter. Anyways, as you continue to cool this thing down, you're going to reach some point just above the eutectoid, where you've reached the lever rule and you've got as much of the ferrite phase as is thermodynamically favorable to form, right? So here's all of your ferrite phase. As much as it wants to form is now formed along these grain boundaries. Now, so this is temperature just above the eutectoid, okay? When you go below that eutectoid, right, at temperatures below the eutectoid temperature, you've still got those regions for the most part intact, right? So all of that proeutectoid ferrite, remember, proeutectoid is the eutectoid solid that's forming before the eutectoid reaction. So the ferrite is part of the eutectoid reaction, and this is the proeutectoid phase. But then you end up with the lamellar in between, okay? So that would be an example of a hypoeutectoid alloy. How would the hypereutectoid look different? Well, instead of having alpha here and a mixture of alpha plus Fe3C, the only difference if it was hypereutectoid is that this would be Fe3C instead of alpha for that one. That would be the only difference. So we've got some examples on YouTube. I'll put these links to the homework problem, and you can see some nice examples in the book about how these would happen. Okay, so that is phase diagrams and drawing these microstructures. Again, we'll talk more about it in a later chapter when we dive into the different kinetic impacts on the steel phase diagram.